So hey everyone, and welcome to LINCC Talks. My name is Colin Ryan Chandler, and our co-host is Mi Dai. We are both LINCC Frameworks project scientists. I'm at the DiRAC Institute at University of Washington, and Mi is at University of Pittsburgh. LINCC Talks include presentations and demonstrations that showcase work done by the broader Rubin software and archives community with the goal of further enabling LSST science. And unlike traditional talks you might hear at a conference, tech talks highlight the technical aspects of the work being done. We hope these talks provide a useful forum for a range of groups and authors to present, learn about, and discuss efforts of interest in analyses of LSST data. LINCC Talks are delivered virtually every second Thursday of the month at 10 a.m. Pacific. So today our speaker is Raphael Shirley, and it's going to talk about photometric redshift using template fitting in the era of Vera Rubin Observatory. This is a project that was selected as a LINCC Incubator Award E. Raphael's at the Planck Institute of Extraterrestrial Physics currently, and previously served as an LSST survey scientist at the University of Southampton. Please ask your questions in Zoom or in the LINCC Tech Talks channel on Slack. On Zoom, you can type questions in chat or raise your hand, and we'll take questions at the end. As a friendly reminder, these talks are being recorded and they will be posted on YouTube at a later time. And so without further ado, Raphael, please take it away.
Thank you. I'll just share my screen. Can everybody see that properly?
Yeah, looks great.
Fantastic. Yeah, thank you for the introduction. It's a pleasure to talk to you today. My name's Raphael, just to remind you. I've been working with Mara Salvato, Olivier Hilbert, and Joan Cointanugi, who are all based in France, and we're developing the LaPhare code. And I'm going to talk about that, but actually some more general thoughts about photometric redshifts in general. But really my focus is on photometric redshifts for the Rubin Observatory with template fitting. So I just thought I'd start with a picture of the observatory. I'm sure you're all familiar with it, but it's a sort of extraordinary observatory that's currently under construction. We're hoping to get data next year, or even the first photon very early next year. Like I said, I think most of you are familiar with the observatory, but just to make it clear, that's the focus of my work. Some technical details. I don't expect you to see all of these or read all of them, but sort of some key features. It's got an 8.4 meter primary mirror, and it's going to reach these extraordinary depths in the 10-year survey up to 26 magnitude in the I band. This unprecedented data set is going to require photometric redshift for I think most aspects of extragalactic science, which is my focus. So a little bit of news. I don't know if you've seen this image. It's from around a week ago. This is the secondary mirror M2, and you can see at the top here, it's been loaded onto the telescope mount assembly. I find this image slightly complicated. It's kind of looking through sort of from the perspective of M1, M3 towards M2 up here in the top. And this is a kind of platform of the engineers putting it on the telescope mount assembly. So I work on the German in-kind contribution. This began in April 2023. And a key element of it is the LaPhare, the code. LaPhare is actually French for lighthouse. And it's a template fitting code. And this is previously concentrated on galaxies. So we're building on the experience with active galactic nuclei from various other fields and surveys and trying to improve the performance for active galactic nuclei. eROSITA has been a key focus of our work. This is an X-ray telescope, but we want to build a general purpose code for photometric redshifts, particularly for Vera Rubin or the Legacy Survey Space and Time, LSST, with just these UGRIZY optical bands. But I think a lot of people are using it for much more multi-wavelength coverage, and that will be important in the deep fields of LSST as well. And yeah, I'm concentrating on the AGN capacities. I'm going to speak a little bit about AGN in particular, but most of my work is also useful for galaxies in general. A key feature of LaPhare is that it fits galaxy templates, AGN templates, and stellar templates at the same time. And we're not performing large-scale production runs as part of the in-kind proposal, or when we're not sort of duty-bound to provide those. I'm sure we will be running it at fairly large scales, but obviously we're expecting the code to be run at scale by other teams or other groups, and a key part of it is performance at scale. So yeah, it's just a picture of the eROSITA Sky. If those of you aren't familiar with it, it was an all-sky X-ray telescope. Unfortunately, due to the war in Ukraine, It's actually stopped observing. So the telescope is in the sky and hopefully will restart again, but that's somewhat uncertain. But we already have around half of the survey that was expected to be performed, and the sky was actually originally separated into a Russian and a German half of the sky, and the German half for the first data release is public. You can all use this, and this is giving us very large AGN samples. We have around 900,000 samples in the latest release, much more than that in the deeper releases, which will be made public in due course. So that's the focus of my work, but it's not of direct relevance for photometric redshifts. Often we have these samples of X-ray objects, but we want photometric redshifts for them to do science with. And we're going to get some of those photometric redshifts from LSST. So for us, that's why LSST is so important to us for the X-ray samples we're getting. But in general, the code will be useful for lots of other science purposes. So I keep skipping. So I want to start with a question, really, which is templates or machine learning, and I want to consider some of the pluses and minuses of each method. So machine learning, I'm thinking the sort of key advantage has very high performance inside the training space. I think that's sort of indisputable. It's very hard to beat some of the machine learning codes with template fitting for a given training space. It's easy to use additional inputs. So typically with template fitting, we're just looking at colors for total photometry. But with machine learning, we can consider other features, morphology measurements, or even pixel data. And it's sort of a general method for taking a given input space and turning it into an output space. Whereas template fitting, we're much more thinking of total fluxes in a given band. It's fast to run after training, so there's a limitation in the computational time for training, but once we've trained, it has a very quick per object time, which of course, when we're dealing with huge numbers of objects, as we will get from LSST, is crucial. I think it's fair to say it has arguably poor handling of rare objects or objects that aren't in the training space. And I think I'm going to be a bit more quantitative later in the talk and talk about what I mean by that exactly. But essentially, we have to, if we're interested in studying a given object, it has to be represented in the training space. And that's well understood limitation of machine learning. And it requires retraining on new data. So if we have a new version of the survey with improved noise performance, deeper data, it has to be retrained. We can't simply run it on the new data without retraining. Template fitting, on the other hand, is physically motivated. We have these physical models of the spectral energy distributions of the objects. We have no training set required, essentially. That's not entirely true. We can do things like 0-point offset calculations, which is a form of training, but essentially we can perform without any training. And I think that's particularly important for completely new objects. I think one of the most striking examples of that is the high redshift objects in the JWST imaging, where we don't have training sets for these objects. We don't have spectroscopy for these very high redshift objects, and that's where template fitting can be very useful. And we therefore don't get a training set bias as well. I will speak about that more later, I think. So we can probe new regimes with that, and it's statistically robust. It's based on chi-squared statistics, can be extended to Bayesian statistics, and I think it's fair to say those statistical methods are well understood. I think we're learning more about the statistics of machine learning, but some people were critical of the statistical robustness of it. I think it's the only method for small samples. So if we're really dealing with small numbers of objects where we cannot train, it's the only method we have. So I'm going to talk about some challenges with SED fitting for AGN in particular, but I'm also going to make some general points about how photometric redshifts work. So on the left here, we have the Matthew Temple model. This is an AGN model. So we've got wavelength on the x-axis against flux on the y-axis. And we're seeing an AGN at various different redshifts. And the key feature of AGN spectra is they have this negative power law slope. So we sort of the main continuum here is just a downward slope, and then we therefore have essentially complete degeneracy between redshift and luminosity. So we have to depend on other features. So we depend on either the Lyman break moving into the bands here, which only happens at higher redshifts, or we depend on these broad bands, which are hard to track that their impact on the color space. So unless we have the near infrared or far infrared where we can start to catch this warm dust here, we do tend to get lower performance for AGN, and that represents a real challenge for photometric redshifts with AGN. So photometric redshifts in general are based on color redshift relations, essentially. So there are 4 plots here. The top is for point sources, and the bottom row is for extended sources, and these are all AGN. And the black dots are spectroscopic redshifts. So we have, again, redshift on the x-axis in color. So on the left, it's I minus Z color, and the right hand is W1 minus W2 color. And what we're really doing is we're looking at the relation between that color, which we measure, and the redshift, which we're trying to estimate. And I think this sort of really demonstrates the difference between machine learning methods and template fitting. If we think of machine learning methods, the straight lines here, which are the template colors, are completely unknown. They don't go into the training at all. We just have the black dots, the spectroscopic sample. So we take a given color and we look across the redshift, and we can get a distribution of redshifts from the training sample. But of course, there are regions of this color redshift space which are not well sampled by the spectroscopic measurements, and that's where these templates possibly can come into their own. Perhaps in this high redshift region, we don't have good coverage with a spectroscopic sample. Obviously, spectroscopic samples tend to be have a fainter, they tend to be brighter objects in general. They don't go to such a high depth. And that's sort of really, I think, giving you an idea of the difference of the 2 methods. This actually is from Mara's 2022 paper of AGN samples from eROSITA. This model has been very important, I think, for the AGN community. It's been used to study AGN and look at the color spaces, the color redshift relations that we expect to get for Rubin and Euclid together. Actually, I think for AGN, Euclid is going to be very important. It has continuum emission from the accretion disk, various other features from the AGN, and that's something that we're currently implementing into LaPhare, where previously we just have a sample of AGN measured spectra was actually built from a set of SDSS spectra, and it has a series of parameters, so it's much more a parameterized model rather than a set of templates, and that's sort of one aspect of the work we're doing going forward. So LaPhare, just to give you a bit of an overview of the code, I mentioned it's French for lighthouse, actually an acronym, I think, photometric analysis for redshift estimation. It was originally a Fortran code going all the way back to 2011. It's quite a mature code, and it performs spectral energy distribution fitting using a set of templates from spectroscopic measurements. There's a new C++ version, which is here. This is the official version, which we're still recommending people to use, but a key part of the LINCC Incubator is moving that, is transitioning to a new version of that, which has been sort of the focus of my work in the incubator, and I'm going to speak about shortly. There's a Python interface, so it can be run via Python, and it fits stars, galaxies, and AGN separately, and essentially is performing chi-squared fitting for every template, and then selecting the model with the minimum chi-squared overall, or marginalizing over the templates to give a more of a Bayesian posterior on the redshift. So the LINCC Incubator, that's the main reason for me giving this talk, and like I said, has been the focus of my work. It was called LINCC Incubator LaPhare. I'm not going to go into too much details about LINCC. I think you're all working either with or for LINCC, so you know what it is. But it was a $22,000 grant, and spent 3 months working with principally 2 software developers, Drew Oldag, Olivier Lin, as well as Jeremy Kubica, in addition to Joanne Cohen-Tanugi from our side, and others, including Alex Maltz and others. This is from February to May 2024, and it was a C++ Python rebase. So one of the technical processes was moving from GitLab to GitHub. I think this was a really positive change. There are lots of features in GitHub which weren't present on the private GitLab repository that we were using before. And a really important aspect of it was the continuous integration and continuous development, particularly with Mac deployment. And this has been extremely useful to us. I've got to really say a really big thank you to particularly Drew Oldag, in addition to the other engineers, Olivier Lin, Jeremy Kubica, it's been extremely helpful to us, and I think we've gained a lot from it. I think the incubator has been great for us. So thank you, really. We also worked on the Rail interface via Python. This was a sort of feature of some of my work with the in-kind contribution. It's important here to be sort of very clear about this dividing line between the work there, that my in-kind contribution has really been focusing on the AGN development of the code, alongside some of this work on the Rail interface. But the LINCC incubator was really focusing on this, the code elements, the code development, particularly this CI and CD, and that's very much distinct from the in-kind work. One of the things I'm really excited about is the pip install LaPhare. I really think this is going to make the code much easier to learn, and it's going to make it much more useful to more people. I think that the current sort of cohort of PhD students, they all sort of come from Python land. They all use Python, and I think pip install LaPhare has really helped us, particularly with the compilation of the C++ sort of base code that the code is written in. That was a real struggle to get that working for various Mac distributions. And I think that's something that I certainly couldn't have done myself. So I'm extremely grateful, as I said, to Drew Oldag for all the work there. But pip install LaPhare is a really big win for us, and we're really happy with that. And a slightly minor point, but we developed a logo and printed stickers as part of the incubator, and I think that logo that we developed, I think, is very helpful to us for promoting our work. So it's a minor thing, but it's very useful to us. So Rail, what is Rail? It's the Redshift assessment and infrastructure layers. I think a lot of you will be familiar with it. It's essentially a whole set of software for calculating redshifts at scale, including the assessment. So it's not just a sort of infrastructure for really running redshifts on large numbers of objects, but also assessing the results. So here on the left, I've got a posterior redshift distribution. So these are the results of almost all redshift codes. We have a posterior probability distribution in redshift space. We can perform point estimates from that. And this middle figure is then looking at point estimate performance for a sample of AGN here, but it could be galaxies or anything. And then these probability integral transform plots, where we take, for a spectroscopic sample, we take essentially the distribution of the integral of the posterior to the truth. And this is it's a really good way of seeing the performance of the full posterior as opposed to just the point estimates. And this effectively should be flat. If we were sampling from the posterior, this would be a flat distribution. And we're using this a lot for checking whether our posteriors are under dispersed or over dispersed, which I think is a particular issue with template fitting, where we a kind of an implicit assumption of template fitting is you're assuming your model is the true model in some sense, and therefore it doesn't include a notion of model error. So you'll only have your observational errors, and you can therefore get under dispersed posteriors. And an example of that is here on the probability integral transform pit plot on the left. And they say the way to remember it is that if this looks like a U, it's under dispersed. And like I said, it's what that's showing is that your posterior is not capturing your full redshift distribution. So we get a set of posteriors for our redshift sample, and then we find that our true spectroscopic redshifts are often outside. Sorry, my slides keep skipping forward. And we've been using this to essentially broaden the posteriors or calibrate the errors. So in this posterior on the right-hand side, the blue line is the posterior which comes out of LaPhare by default. And we can broaden this using the pit plots to calibrate it, to essentially calibrate these to flat. And that makes our posteriors more accurate in terms of capturing the errors and improving that performance, which I think is a really important part of getting what you might think of as more a true posterior, which also encapsulates the fact that the models are not fully representative of the spectroscopic sample. So here's some results, and I've been running on the CLAUDES dataset. So the CLAUDES is the Canada, France, Hawaii Telescope, CFHD, Large Area U-band Survey. So it's a very complicated acronym, published here in the Desprez paper. And this is UGRIZI data. So previously we were looking a lot at hyperspeed primecam data, but this edition of the U-band makes it more like LSST. And I think we're very keen to be testing against real data, essentially. So I know that lots of testing has been done within Rail on simulated data, and that's obviously great, and we'd like to do that too. But I think we're trying to run on this real data where we can really see performance. And just the LINCC Incubator allowing us to put LaPhare into Rail has made it much easier for us to compare against the other machine learning codes. Here I'm looking at the KNN and the FZ Boost machine learning codes. I'm including BPZ here, although this isn't a fair comparison because this running of BPZ, the other template fitting code, which is in Rail, is actually based on the LSST filters, and I'm working on modifying BPZ to take their proper filters. So it's not a fair comparison, but just to say we are comparing against BPZ, and that's also useful for benchmarking template fitting. We know and we expect to get better performance with the machine learning codes in these training samples, but it's good to have another template fitting code to really for bug checking, just checking the results, and also just to have a comparison. And then here the same figures for AGN, and as I said, we know and we expect we're getting lower performance. So we're getting above 10%. These are approaching actually 20% outlier rates, and lower performance for AGN. That's all well understood and expected. But it's been very useful to have KNN and FZ Boost as benchmarking codes. It's really useful for testing the parameterization of LaPhare. That often we might get a certain outlier rate, and we don't necessarily know if that's reasonable performance, but having the machine learning codes, which are completely independent of any templates, has been very useful for us for our benchmarking, and that's a real power of Rail, which is part of the work that has come out of the incubator. So I mentioned a sort of key question about machine learning methods being that they depend on your science being done in the same training space. So what I'm looking at doing now is degrading the training samples intentionally, and then seeing how that affects performance. So here what I'm showing is a very simple plot. It's just the I-band magnitude distributions for this Claude's data set, which we're testing on now, and obviously showing that your magnitudes are peaking at a much fainter object. So we're going almost to the 27th magnitude here, again approaching the kind of LSST 10-year depth, whereas our spectroscopic sample is peaking at around 22.5 in the I-band. And actually this is on Cosmos, where we have especially good spectroscopic data. So, do you want to limit your science work to these sorts of magnitudes? Do you want to put a cut on your spectroscopic sample and choose your samples that way? I think that's it will be a real shame in some ways, because we're not necessarily harnessing the full power of LSST, where we're getting these incredible depths. And I think so. I want to see what impact that has in order to understand where LaPhare can maybe be useful, where we move beyond the training spaces. And another thing I'm doing on this Claude's data set, because it's Cosmos, we also have multi-wavelength data from the Cosmos survey, and that excellent multi-wavelength data can be used to get LaPhare redshifts, which can act as a kind of truth, where we normally use spectroscopic samples. If we alternatively have very good multi-wavelength coverage, those samples could also be used to train machine learning methods, or if not, just to benchmark the template fitting methods using the UGRIZI bands only. And that's another advantage of LaPhare, and also I think could be useful to the other codes and the people using Rail, is that we can provide these other possible training sets of high quality photometric redshifts over a larger magnitudes range, essentially. So here, one of the sort of first things I did was I simply just cut that training sample in magnitudes. So I did the train test split. I took this spectroscopic sample and did a 60-40 split on it. And I then just degraded the training sample, but left the testing sample as it is. And as you'd expect, obviously, when you're only training on I-band 20 objects, but you're then testing on I-bands up to 26 even, we obviously just lose all these high redshift objects. And I can take a question now if you want. See a hand up.
Yeah, just asking, when you did this, were you only doing the KNN in color space, or did you use magnitude also?
This was using what I think is a standard method for KNN. So I think it's just it's KNN as it's set up by default in Rail. So I was sending it magnitudes and errors and using it in the default way.
Yeah, because
So,
the performance may be very different if it's trying to match in magnitude 2 versus just matching in colors.
right, okay, yeah.
I'd be good to check that.
That's interesting. Thank you. I'll try and that could explain why you're not capturing some of the high redshift objects, and I'll definitely look into that. But this has been an important test for us anyway going forward, and we're going to keep doing these tests on the degrading of the training space. The next step is to also use these possibly sort of multi-wavelength photometric high quality truth tables to do similar comparisons. One of the things I'm working on at the moment is a generalized prior via the Python interface. So previously, LaPhare had the Benitez 2000 N of Z priors. So that is essentially as a function of the I band magnitude, you put a prior on the N of Z. This is some work going all the way back to 2000s, but it has been shown that for data sets with low wavelength coverage, this can be important, or with high errors, this can be important for constraining redshifts. But we've only so far had that in addition to absolute magnitude priors. So absolute magnitude priors, you literally just put a hard limit on the absolute magnitude, and then for a given template, you calculate the absolute magnitude in a given band, and you can essentially use that to rule out certain redshifts dependent on the template. But what we're looking at the moment is using machine learning priors. So we might, for instance, use machine learning codes to get the redshift distribution, but then use LaPhare to get physical parameters of the galaxies. So this is another benefit of template fitting, that we can use it to get physical parameters such as star formation rate, stellar mass. We can then take the redshift from machine learning, which might be superior, and we can get those physical parameters. And implementing these general priors has meant some work in the Python code. I think that's done now. We're sort of, it's a branch available on GitHub, but we haven't merged it yet, and it still needs testing. But we have implemented the possibility of a general prior, and that doesn't necessarily mean just putting a prior on redshift. You could put a prior on stellar mass, or in actual fact, any feature of the template. You could put a prior on templates. You could say, we understand that point sources, for instance, for AGN are going to likely to be dominated by the AGN, and therefore we only use these templates that are dominated by the AGN, whereas perhaps extended objects can have more of a host contribution, and therefore we include these other templates with a host contribution. And that sort of general capacity to put a prior on any feature of the templates and features of the templates, I think is a useful thing which I've implemented recently. Just a note on the philosophy of priors. So we know that they can improve metrics, but I think that there's a danger that they can detract from the fundamental purpose of SED fitting. So for instance, one of the things that the Rail BPZ can do is you can fit an N of Z from your training sample. Now that will improve performance on that training space. But then, of course, we know that training space is not necessarily representative of the target space. So there's a danger of this so-called Goodhart's law, where you define a metric for measuring performance, then you end up chasing the metric rather than the actual thing of interest. So there's a danger of using priors with template fitting, I think, but they're certainly useful, and I think it's an important part of the work that we've implemented them. Yeah, I think that's basically done this work now, and is available on the GitHub code. So SED fitting for classification is another possible use of the template fitting. So previously we've for instance, use point sourcedness to make a distinction between galaxy and hybrids and quasars. So I think, as I mentioned, extended objects are more likely to be nearby and have more of a host contribution. If they're point sources, they're more likely to be real quasars where you're dominated by the AGN. But we can, of course, use this template fitting to classify objects. So we have these sets of quasar, AGN, and stellar templates, and we get this sort of classification for free in a way. So we're hoping that if we're lucky enough that the Rail LaPhare is included in large-scale runs, we will have these additional features from LaPhare, where we have this chi-squared for the various models, and those chi-squared can be used for classification. And again, have to be sort of clear here. This is some ROC curves. These are receiver operator characteristic curves, the sort of classic curves for looking at performance of a classifier. So again, just using an off-the-shelf neural network classifier, we do see higher performance of that classifier. So this is trained on the Marchese. It's an AGN sample on Cosmos. and just showing how the kind of classifier performance we get on just UGRIZZY data from this Claude's data set I've mentioned before. And again, yeah, like to be clear, the machine learning codes and neural networks are outperforming. But of course, we can do the LaPhare classification without any training set. And I think this could be useful for the sort of full LSST data, again, where for every object we have a chi-squared for the AGN and the galaxies. So there is some classification power there that can be useful, and that's sort of how we're trying to sell LaPhare for the large scale rail runs. I'm really hoping that it is included. Some other work I've been doing recently is working on these particular machine learning codes. This is Circle as a code. It's a paper we put out this year by first author Aman Saxena. So there's a lot of detail on this slide, but the top is showing the basic architecture of the code. We're putting in morphological data in. So we know that, for instance, the galaxy spectra is more informative for Redshift than the AGN. So by including aperture measurements, the machine learning can effectively learn to ignore the central point source or be aware of the fact that the outer edge of the galaxy has more informative color features, and this can really improve performance for AGN. And again, we were outputting posteriors and then using these pit plots and point estimates. And circles has not been implemented in Rail so far, but I'm working with the PhD students here, and I think I feel like now I've done it once, I think I can persuade them to do it for their own codes. And I think sort of that LINCC Incubator has sort of taught me how to use Rail and how to develop Rail, and I'm hoping that will sort of allow me to kind of spread the word and get other people to include their codes in Rail, which might therefore sort of increase the utility of Rail and lead to other codes being available. This, of course, depends on other additional data being fed into Rail. So I know that the standard off-the-shelf methods are taking magnitudes and errors, but it obviously is a flexible tool that can be used to take other things in addition to, for instance, aperture measurements. Or another code we're working on, pixels. This is another PhD student, William Roster, and this here we're using full pixel information. So I think in the group here we are developing lots of machine learning methods. And again, this hasn't been implemented in Rail, but I'm trying to persuade William to implement it in Rail. I think, like I said, now I've done it once, I think I could do it quite quickly. And I think that advantage of Rail of allowing us to quite straightforwardly put other codes in with a generalized framework for calculating redshifts is really powerful and useful. And here just showing the performance of the pixels code from William Roster, and showing how that pixel information can really help us get improved performance from the template fitting only. And again, this is with optical and near infrared and near infrared, mid-infrared, which is very important for us in AGN science. And actually that's going to lead me on to my next topic, which is the impact of the JH KS bands for AGN. So here's some figures from Gomez et al, essentially just showing, and this is spectroscopic redshift against photometric redshift, just the performance of point predictions, and just showing that these near infrared ZY JHK bands from in this case Vista can help. And I previously worked on a UK project to joint process this Vista data with LSST, and I think those programs are really important. So not just Vista, which is going to cover the whole southern sky alongside LSST, but also WISE is of crucial importance for AGN. And although like a lot of people are going to be doing science with LSST only, these data sets are extremely important in the deep fields where we have excellent deep data from other surveys. So here's some other images from where. Here is VHS. This is the Vista Hemisphere survey, which again, it covers the whole of the southern sky, so it's most useful for LSST science. This is some work with DES data, but similarly where you have effectively a deeper optical data, but you're trying to use shallower VHS data, and showing how objects that are in DES are often real objects in VHS, even going down to low signal to noise. So these signal to noise 1 detections in VHS, which you might not be considering robust if you didn't have the optical, we can confirm them with optical. And also we then get this additional color information for constraining. Like I said, I worked on an in-kind proposal, which is doing this forced photometry using actually the LSST science pipelines. I think for various science purposes, that's going to be very useful. And of course, those additional bands can be fed into rail. And on the deep fields, we don't just have near infrared, we have much wider multi-wavelength coverage. And here again, just some information on the number counts. So just showing how if we look at the K band, which from the VHS only catalog is peaking around below 20th magnitude, but by forcing these deeper DES or in future LSST positions, we can sort of extend the number counts and start to pick up these low signal to noise objects from the near infrared imaging, and again the importance of that work. Here's some depth distribution. So this is some work I did previously on deep Herschel fields, but it doesn't really matter that they're the Herschel fields. This work can be extended to LSST. And what we're seeing here is a wavelength on the x-axis and the 5 sigma depth, effectively magnitude on the y-axis. And each of these violin plots is a distribution of pixel depths on the sky. So, for instance, I think this is broadly dominated in this case by pan-stars. We also have this much deeper hypersea prime cam features here. But what this is showing is that the complex interaction between the depth of each band and a given, so this is a starburst galaxy, that doesn't really matter. But what we're seeing here is if we know, for instance, that these JHK bands are giving us additional performance on the photometric redshifts, we have a complex relation between depths here. So if we want to take a sample which has detections in those VHS bands, we might be limiting the effective depth we can push in the optical bands. That makes obviously the selection functions much more complicated. So I think my work forcing photometry from LSST to VHS is useful there, because a key feature of the LSST science pipelines is that an object detected in any band is measured in every band, which means you can sort of design your selection functions to suit your science case. But we do have to be very careful, particularly for AGN science, about requiring near-infrared or mid-infrared data in order to get good photometric redshifts, and therefore effectively limiting the depth and not making full use of the LSST data. I think for some of our AGN samples, for the E-Rosita samples, for instance, those are bright objects, that's probably fine for us. But if we're looking at the Theta AGN, maybe we've got variable AGN selected from LSST variability, we have to be careful about requiring detections in those bands, or indeed using those bands, but being aware that we only get good photometric redshift performance when we have detections in those bands. I think there's a lot of work to be done on modeling those selection effects. It was a real challenge actually for this work we did on Herschel. Modeling selection effects was really challenging for designing samples of photometric redshifts that are reliable and modeling the selection. So yeah, just to show you these VISTA surveys, so I do think this is important. So this is the VHS survey covering more or less the whole of the southern sky. I think that's again emphasizing its importance for LSST science, and again going to some details on those LSST surveys, in particular the VHS survey, which has this very wide area coverage, which is going to, I think, 20th magnitude in K, and that's for AGN science. That's very important. So I think I won't go into. I think I'm at 40 minutes now. I won't go into too much more details on that work on the joint processing, but just to show you some examples. So this is a cluster, a redshift 1.8, which was detected using the VISTA data, and here just showing how. So we've got the GRI full color image on the left. Again, this is from hypersea prime cam, and then on the right we have the VISTA from the video survey, sort of redder side, and showing how that can be used to select clusters, but again, sort of really emphasizing this concern of not wanting to be using these other required data sets for certain science cases to limiting the work we can do with LSST. This is particularly useful on the deep fields where we have very deep VISTA data. And again, here's another example. This is a redshift 6 quasar. So again, we've got the hypersea prime cam Grizzly bands on the top, and then we're seeing that it's showing up in the VISTA Z band and the VISTA Y band. And this can be used, we're catching it in HSCZ as well, but that can confirm the objects. And this was key to finding this high redshift objects. And I think Richard McMahon, Catherine Kalmer, two people at the IOA in Cambridge who I was working with previously, They're really hoping to use this VHS data to find high redshift quasars, essentially by looking for objects that are present in these near-infrared bands, but dropping out of the LSST bands, so that we're catching this Lyman break. That's a really powerful method using LSST data, but with other data sets. And another example here, this is some AGN host galaxies. There are two examples here, and these are both just showing the importance of this VISTA data. And again, using template fitting here to estimate redshifts, but for AGN science in particular, how important that near-infrared data is. And that's a point for me specifically. I'm working on AGN, but I think it's worth thinking about for rail. Are people going to do rail runs, large-scale rail runs, including these additional data sets that are going to be made? That would be amazing. Or if not, it's a great thing that the rail code exists to make these large-scale runs performable by other groups. And in fact, even perhaps for our own science purposes, if we've got some more samples, we can run rail here locally. But yeah, I just want to sort of highlight some of that work and how important it is. So just a brief note on future work. I think that we're looking now at optimizing the hyperparameters for performance and speed on LSST. So the LINCC Incubator helped us to get LaPhare running within Rail, and that's allowed us to now quickly run tests with different hyperparameters. Essentially, by that I mean the configuration parameters for LaPhare, which templates we're using, what priors we're using, which line models we use, or which extinction models we use, which extinction values. And there's a real sort of cost benefit aspect there with max runtime per object. So we're really keen to get an idea on, for the large scale rail runs, a kind of how much CPU time per object we're allowed. I think for the machine learning codes, they're very fast after training. That's not so much an issue. But I think we really, we want to make sure that LaPhare is included in large scale runs, and we're aware that these template codes are much more expensive. So we have to both justify the utility of that, but also do work to sort of finding a sweet spot between performance and costs. And I think some of that is simple things, like for instance the Redshift grid. We can obviously use a sparser Redshift grid to make it faster, but at what point does that lose some of its utility? And that's the work I'm really concentrating on now with the Claude's data set. So on this, as I mentioned, on the Cosmos field, where we have this excellent multi-wavelength data, but we also can use just UGRIZI. And that's hopefully, this paper is hopefully going to be submitted soon. And this is that work, running LaPhare through Rail with these comparisons that we can very easily get by using Rail with the same data sets. But the purpose of this paper really is to present a kind of recommended settings for LSST, which is going to be as a feature of allowed runtime per object. So I think we probably have to have a set of recommendations of, this CPU time per object, we recommend this Redshift grid and these features and this number of templates, but we can also have a kind of minimal setup for very quick runs. So just to conclude, so I'm working on a 3-year in-kind contribution. This is the German in-kind contribution to LSST. This is how sort of all these European teams are hoping to get access to LSST data. It's a really important part of European contribution to LSST. And I've been concentrating on the prior and AGN science in general. This is now implemented, but we're testing it at the moment. A key part of my work in the last sort of 6 months was these 3 months that I spent partly in Seattle, partly working remotely with the LINCC Frameworks Incubator. And I'm really emphasizing pip install LaPhare. That covers a huge amount of work on various aspects. But this was very helpful to us. And just to really reiterate, very grateful to Joel Dag, Olivia Lin, Johnny Kubica, all the others that helped. And of course, grateful to DiRAC and UW for hosting me for those two sessions. That was a great experience, and I think we got a lot of very useful results out of that. In particular, LaPhare has been incorporated into Rail now. That's really helping us to run tests, and I think just like I've been comparing against machine learning codes much more because they're there and it's very easy to do, and that's all because of Rail, and it's been very useful to me. And yeah, just the work going forward is optimizing templates and parameters for LSST for galaxies, which I think is the main focus of most people's interest in I'm guessing the people here, but also in particular for AGN for me, and how those two things work together. So I think I'm at about 45 minutes there, so I think that's a good time to stop. If there are any questions or thoughts, I'd be very happy to hear them.
Awesome. Thanks very much, Raphael. Yes, we do have a little bit of time for questions. You feel free to ask in Slack or in chat here, or raise your hand, as Jeff has. So why don't we begin with Jeff?
Yeah, I just wanted to follow up on my question from before. So I dug into the rail code, and it looks like the KNN uses colors from successive bands, but also the magnitude in a reference band to find the nearest neighbors.
Okay.
So once you're 5 magnitudes different in the reference band, that distance is just totally going to dominate over the color distances.
Sure, yeah. That makes sense. Thank you.
I think it may be necessary to add a little flexibility to the KNN to use only colors or something like that. Add a parameter to make the comparison more useful.
Mm.
Because otherwise the neighbors just aren't, they aren't similar in color space.
I'll look into the developers of the Rail KNN and ask them if that's possible within the current code, or if not, yeah, look into implementing it.
Looking at the code, it'd be just a few lines of change.
Okay.
Yeah, because KNN wasn't really meant to be a real algorithm. I wrote it in an afternoon to be like a 10% effort, 90% results sort of thing. We can add that switch in like 10 minutes, I think.
Yeah, I think it'd be easy.
Yeah, I think it was there originally and we took it out for some reason. I don't know why, but yeah.
So I think that my understanding is that for the desk work, the N of Z is obviously the crucial output they're looking for. So I think that's really important. I'll be really keen to look into that, because I think one of the sort of key claims or assumptions we're making is that LaPhare might be able to be competitive and useful for the N of Z measurements where we don't have coverage of the fainter magnitudes in the spectroscopic samples. That's really important to us. So if it's the case that we make this change and that sort of goes away, and we can recover, we can train on a given N in Z, and we don't get a bias towards that N of Z, that's important for the machine learning codes. But
I don't think it'll go away, but I think it will reduce the effect.
Okay.
Great, thanks for that. Getting some positive things out of here already. April, go ahead.
Hi, well, can you hear me?
Yeah.
Okay, good. Sometimes my microphone glitches out. Well, thank you so much for the talk. I'm relatively new to astronomy research and programming, so I was wondering, for the LaPhare code, I understand how the template fitting picks the template based on the lowest chi-squared, but where do those templates come from in the first place, and kind of what physical concepts and data are they generated from?
So there are different sets, but broadly they come from spectroscopic measurements. So spectroscopic measurements of actual spectral energy distributions of real objects at a given redshift. So essentially for AGN, there are some particular questions there. Like for instance, I mentioned the AGN has this power law continuum. So we take spectra of a set of AGN, we get a set of spectra, and we use those spectra to build the templates. But the point at which the Lyman break kicks in, where all of this at the shorter wavelengths, the higher energies, where you're essentially losing all of your photons at some point. The point at which that happens is dependent on redshift. There are other things like, for instance, the intergalactic medium, which is attenuating the light depending on the redshift. So there are aspects of the model which are dependent on the redshift, like the intergalactic medium. But broadly, the actual spectra themselves are real measurements of spectroscopic objects, where you really have a very high wavelength resolution set of measurements and a real, like a true SED essentially. But you can also take other models generated in other ways. So for instance, we might want to generate a set of templates with a given AGN fraction, and we have a separate AGN model and a separate galaxy model, and we generate templates by adding them in at given fractions. I think one of the features of LaPhare is that it fits one model at a time. So it really does just take a model and it scales it to fit the photometry, and then that model has a set of physical parameters or other features. But it's not a kind of parameterized model so much. So we have to generate those beforehand if we want to take a more parameterized model. Yeah, I hope that answers the question.
It does. Thank you so much.
Great, awesome question. I'm going to interject with a host prerogative question here. Just a quick question. You mentioned resources like the CPU usage, and I think just a lot of us would like to know, broad strokes, what kind of resources are you using now, and what do you expect that you need? I think you mentioned CPU, but not GPU. What are you expecting for LSST you're going to need to do this?
So for LaPhare, we haven't been testing on GPU and don't expect to get, I think, big performance increases from GPU. Obviously, it's a completely different story for the machine learning codes based on images, where I think it becomes really important. But so we have our own high performance computer here at MPE. But I think that's more of a sort of a question of what the large scale runs expect to be doing. I think that we don't expect the large scale desk runs to cater to us, but what we more want to do is persuade them to include LaPhare. So I think that's more of a question from us to you in a way of what machinery are you using to do the large scale runs, and what can we do to make it more likely for you to include LaPhare in those runs? I saying you, I mean desk, the Dark Energy Science Collaboration, and the people that are going to be performing those large scale runs.
Yeah, no, that's great. I just wanted to clarify, wanting to insert this in existing runs.
Yes,
that's
sorry,
great,
I can't
great to
be.
hear.
Sorry, I can't be more quantitative.
No,
but
that's fine. Sam, you have your hand raised. Go ahead.
Yeah. So again, some of the template methods can be a little slower and things, but for smaller samples of objects, some of the science cases don't need to run on billions of objects. And one of the groups that's really interested in LaPhare is the supernova group, who will not have as many objects. We may be able to run even on like bigger template sets or something for that. And one of the things they're really interested in is the physical parameter estimates and interpretable SEDs that come out of that. I haven't used LaPhare much. Is there plans to output best fit templates and stuff in the Rail version? I haven't played with the Rail version to know if this is even already in there.
Yeah. So essentially, we're when you run LaPhare, you specify what outputs you want, and the Rail is built to set a certain number of outputs. And we were kind of told that there shouldn't be too many, because it adds to, obviously, for every object if you've got a large array of numbers. But that's completely generalizable. So you literally just give it to Rail and you can determine what those are. So for physical parameters such as stellar mass, star formation rate, you have to use a particular set of templates. And that they are particularly slow because you're looping over stellar mass and age and various factors. So I think one of the ways, for instance, we've been using that is by using LaPhare or another method to get the redshift, and then using LaPhare at a given redshift to get those objects. But they can absolutely be output. You just have to specify the set of templates that allow you to do that. Essentially the Bruce-Wall and Charlot templates, and then you have to tell Rail to output those quantities that you want.
Perfect. I'm going to start playing with this today. So I'm very excited about this. This should be very, very nice compared to BPZ, which does not do these physical parameter. All right, thank you.
Awesome, great. Yokabin, if you want to ask a question, you have your hand raised. Time for
Yeah, thank you. I think you might have mentioned this a little bit earlier, but what exactly are the requirements for signal to noise and the number of bands for photometric redshifts to be a viable alternative for spectroscopic training sets?
Okay, I'm going to struggle to be quantitative on that question. That's part of the paper that I'm working on at the moment. So I think what I'm looking at is the difficulty I've had so far is which sets of requirements on which bands. So what I'm currently looking at is photo-Z accuracy as a function of signal to noise in R band and the K band, for instance. But obviously I can look at all pairs or various different factors. And I think I'm sort of working at the moment how best to plot that and quantify it. So I sort of, the only thing I can really say to you is that I'd like to get back to you on that question. That's a key part of what we're working on at the moment, is because I think we're hopeful that even for low signal to noise, for instance, if you've even with signal to noise 2 on all of the near infrared bands, if they've all got signal to noise 2, they still can contribute, and even in fact non-detections can contribute, because it's a a zero flux with an error is it still can add some constraining power. But really quantifying that and figuring out how to investigate that is a kind of ongoing question for me, I think.
Okay, great, thank you.
Awesome. Great questions, and sounds like we got some exciting things coming out of this, which is awesome. Let's go ahead and we're going to wrap things up now, just so that we end on time. I do want to thank again Raphael for this awesome talk. Thank you everyone for attending today. The next Tech Talk will be on September 12th at 10 a.m. We're going to be hearing from Annie Zanadakis about Dipper stars and LINCC Frameworks involvement in that project. So please join the hashtag LINCTechTalks channel that's on Slack, and there's the email list, which is link@lists.lsst.org for future announcements. We will be posting this talk on YouTube within the next few business days. And yes, that's it. We thank everyone again so much for coming, and have a great day.
Thank you. Bye.